Let's take a closer look at what it means for a system of knowledge with a bunch of rules to be able to answer a query Q using the process of resolution. We want to know, in other words, whether given this system of rules, which could have a lot of facts and a lot of rules, one can actually infer through logical entailment some way of fulfilling this query. Now, this query might consist of unknown variables such as X and USA and relationship being is leader of. So K implies Q means finding out ways to assign variables to all the unknowns in this query so that it actually turns out to be true given all the knowledge in your knowledge base. So resolution involves, as we have seen before, both entailment, which is logical inference, as well as unification, which is replacing any variables in the query by actual values. Now, remember again that a statement like K implies Q is exactly the same thing as saying that not K or Q is true. We went through this in a little bit of detail a while back. Please convince yourself that whether or not K is one statement or hundreds, K implies Q is still the same as saying that not K, that means the negation of all these statements in the knowledge base, or Q, this compound statement is true. To see that, if K is false, then not K is true. And if K is true, then not K is false. And if not K is false, then Q must be true in order for this to be true. The next important step is to see that not K or Q being true is the same thing as K and not Q being false. Try to convince yourself that negating a compound statement which is the OR of two statements is the same thing as taking the AND of the negation of both of these statements. An easy way to see that is that if check all possible values of K and Q, there are four combinations: true, 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 false, false, true, and make sure that in each case not K or Q being true is the same thing as K and not Q being false. We won't go through that in detail. I'll leave it to you to work that out yourself. Now that we see that in order to prove Q, rather to show that K implies Q, all we need to do is show that K and not Q is false. So what do? We augment the set of rules or knowledge that we have with not Q. That means if we had a statement that is leader of X, comma, Obama is my query, I will augment my knowledge base with a statement that it is not true that is leader of X, comma, Obama. The augmented knowledge base, which is our original knowledge and not Q, must give me a falsehood if I was to prove K implies Q. So in order to show this, one needs to take this augmented knowledge base and crank it through some logical resolution engine which performs both inference and unification, that is assigning values to variables, and figure out whether or not it answers true or false. If it answers false, that is that K and not Q results in a falsity, then the answer to my query is true. K does imply Q, as per this argument earlier. Along the way, we would also have figured out the right values for any missing variables in Q, and in the process answered our query. However, if K implies Q results in a true statement or a satisfiable statement, then the answer to the query would be no, because then K and not Q would be true, which means that not K or Q is false, or K implies Q would be false. This seems fairly straightforward. All we need to do is take our query, even if it contains variables, negate it, that means state its opposite, add it to our bunch of knowledge, crank it through some mechanical process of resolution and unification, however difficult that may be, and see whether the answer comes out false or true, and then we have the answer to our query, along with any variable assignments which would make sure that we get the right answer. The trouble is, this resolution procedure may not actually ever finish. It may go on forever. That's actually possible, in which case we get into some trouble. Resolution need not always work, and the meaning of not working is that it never stops. This brings us to some very important understanding of the fundamental limits of logic and resolution. First of all, resolution may never end, and by never we mean never. Whatever algorithm we might use to perform resolution, it's not the issue that our algorithm is bad, but it may be the case that resolution could never end, and in fact this is the concept of undecidability. There are some cases where you have a bunch of knowledge, a bunch of rules and facts, and you could never tell whether or not that combination of rules and facts is true or false. In other words, they are undecidable. This was actually shown for the case of predicate logic, that means the logic that we've been studying, by a number of people in the early 20th century. Kurt Gödel, Alan Turing, of course, who's the founder of computer science, Church, and a few others, in a variety of different ways. Turing showed it in the most elegant way for computer science perspective by using the concept of a Turing machine. But that's a subject for theoretical computer science, and we won't go into that in this course. The other trouble is that even in situations where the resolution process does come to a conclusion, it might take a lot of time. For example, for n facts with m variables, one might have an algorithm which took 2 to the n m time. That means exponential. We've seen this before, algorithms which take extremely large number of steps, such as figuring out all possible combinations of ones and zeros in a large 1000-bit vector, takes 2 to the n steps. Similarly, logical resolution might take 2 to the something number of steps, which makes it really intractable in practice for a large number of facts. It turns out that if you have just propositions, that means no variables, the old what we just did with just statements like Obama is president of USA, rather than relationships between entities and other entities, such propositions alone do result in decidable logic. That means you can always find the end to a resolution procedure, but it may still not be tractable in the sense that it might take too long. And that comes up to the whole theory of computational intractability, with the notion of NP completeness. And the first such problem to be shown to be provably difficult in this sense was that of satisfiability, which was nothing but whether or not a statement of propositions could actually be satisfied. The point about covering some of these important results in logic and undecidability and computational complexity and intractability is not that they are critical for web intelligence, but just to remind us that if we have a vision such as the semantic web, where we would like to have automated reasoning at web scale, then we will probably come across some of these issues during such an exercise, because we'll have lots of facts and lots of rules. We'll be relying on predicate logic, resolution procedures which may not complete ever, or even if they do, they may be intractable in that they could take lots and lots of time to be effectively undoable. So what do we do? It turns out, fortunately, that some kinds of logics, specifically those designed for the semantic web languages, such as OWL-DL, which stands for OWL description logic, and OWL-Lite, which is an even simpler version of this logic, essentially are decidable. That means they will always complete the resolution process. Description logics and OWL-Lite essentially encode the notions of sets so that we can write down logically a statement that a leader means that that person that is also a person, or a faculty member is also an employee, or things like that. So essentially, statements about the structure of the world are encodable in description logics, which is decidable, doesn't suffer from this problem of undecidability. In its worst case, it's still intractable, though in most practical cases, the resolution procedures do complete in reasonable time. The other piece that is used is something called horn logic, which is essentially rules, such as if there is a person and the person is born in a country C, that implies that person is a citizen of that country. A rule like this is called a statement of horn logic if there's only one conclusion on the right-hand side. If it was, say, a person is born in C, it's a citizen of C, as well as a few other things, then that's not a horn logic statement. Such statements in horn logic are tractable. They will always complete very fast, but if they do. But in some situations, they may actually go on forever. There are ways of fixing horn logic by, with some caveats which we won't go into in detail, to make it actually decidable and tractable. So in practice, what one does is, for a semantic web-like system, one relies on description logics to deal with the structure of the world. That means describe what the elements in the world actually look like, how they relate to each other, and then rely on horn logic to encode the rules. The reason one does this is that the structure of the world is likely to be reasonably small and not necessarily lead to some of the intractable situations, whereas the number of rules one may have may be extremely large, so one needs to rely on something which is provably tractable. Anyway, we're not going to cover either the resolution procedures in detail nor any of the fundamental limits of logic in this course, because what we'll find very soon is that normal logical resolution, whether it's decidable or not, intractable or not, is not necessarily the best way to deal with the real world. And that's one of the reasons why the semantic web vision has sort of floundered in the past decade. And the reason is uncertainty. Regardless of the fundamental limits of logic, the real challenge that logical inferences faced in trying to deal with large volumes of facts that could be inferred from the web is none of these are necessarily true or false. They are true with a certain probability, and that actually causes much more fundamental problems than some of these fundamental limits. Let's see how.